Okay, yeah. And so I don't promise to pay attention to the chat because that like having to try to read the chat significantly slows me down. Um, so if somebody wants me to pay attention to the chat, my preference is for that person to read it out. So yeah, last time we made it to this slide. Um, I wanted to leave a little, yeah, well, maybe I should refresh this slide. So yeah, my four main motivations for this tiling kind of work, um, in terms of like answering the question, well, how do you apply tiling theorems in the real world? There's human to human, like I am an example of an agent that is stretched out over time. And so I can come to understand rationality better by studying decision theory through the lens of these tiling theorems. And this kind of thing can be important for studying AI risk because it can involve tricky decision theoretic problems. And also just like, yeah, I think improved pictures of human rationality can be important to like human organization in a certain way, where like um, the types of rationality that were studied kind of in response to World War II and the Cold War were influential on the like types of organizations that people created. And so similarly, like the types of rationality that we study now might be influential on like our behavior in a number of subtle ways. Um, Motivation number two, which is kind of the easiest one to explain the relevance to AI safety, is the AI to AI tiling case, where we have some system that has some safety properties and we want to ensure that those safety properties are maintained over time. And so we want to study the self-modifying behavior of those systems to make sure that they are not motivated to modify in a way that risks those safety properties. Motivation number three is human to AI tiling. So what I mean by this is like humans are currently in the process of creating powerful AIs. Can we understand this process better through the lens of tiling theorems? And the hopeful application would be like if tiling theorems can get kind of realistic enough, close enough to the real world, that they can meaningfully inform decisions that we make by giving us a theory of like uh, structures of AI that we could build and not predictably regret. Yep.
So I'd understood the core idea of this project to be about self-modification, right?
Yeah.
So where do points 3 and 4 come into that in that case?
Yeah. So I think
Good.
self modification, which is like points number 1 and 2, is kind of the easier case to think about. But what I'm doing here is I'm flagging that the eventual goal to me is 3 and also 4. Like, I mean, all of these do have some real significance, but in a sense, number 3 is the big problem that we need to solve. And number 2 is actually like a means to the end of number 3. And also, number 4 we can see as a means to the end of number 3.
Okay.
So it's, yeah, we can generalize from like this sort of self-modification to this more general trust picture. Roman?
Yeah, I just thought that you can get number three without the number two. You can't trust AI if AI doesn't trust itself, right? So yeah,
Yeah, I
you
think
said
that's
it
right.
yourself. Yes, it is a means to an end.
But also there's the more abstract path of like number two is kind of easier to think about than number three, because number two, we can think about systems that are entirely of our own invention. So we can just think about updateless decision theory, for example, which is what we're doing mainly in these slides. Whereas number three, we need to think about squishy humans. And so three is very challenging.
In the same way, you probably also need one to get four, real, like robustly.
Yeah. And also perhaps three. So yeah, to speak a bit on number four, the idea here is that we can also use a similar picture of this kind of this trust defined by when you would want to change the decision-making process to analyze corrigibility. So my picture here is like the central case of corrigibility is, I mean, you know, there's several different concepts in this cluster of corrigibility, but one of the central ones is when the human approaches the AI with the intent to modify the AI somehow, then the AI should not interfere with this process one way or the other. It should not be like seeking modification, and it should also not be trying to thwart modification. And so I just want to point out that this has like a very similar structure to asking whether the AI wants to modify itself. But here we're asking, does the AI want to modify the human? Does the AI want to manipulate the human? And so taking like all four of these points into account, it gives us a kind of like somewhat symmetric picture of what alignment is supposed to be, as opposed to the usual asymmetric picture, which focuses only on three. Like we want trust between all the participants in this process in a certain sense. Of course, there might be some specific asymmetries in how to set that up. But yeah, I think that's kind of interesting and important. So kind of taking a step back, like I'm about to step into some more formal things. And I want to say some things about how I think about formality. I think we might have covered some of this in like the questions last time, but like any formal result comes with some assumptions. These assumptions will be unrealistic or at least questionable, particularly in the early stages of formulating theories, but even in the later stages. And so I think of the kind of decision theoretic results that I'm talking about in this talk more as sanity checks. I think this applies to a lot of, like, you can think of the Dutch book treatment of probability theory, for example, as an explicit logical argument for probability. But then thinking of it this way causes you to like look at, scrutinize the assumptions and question them, which is good as a way to learn about it, but like also the assumptions are never going to fit the real world perfectly. And there's a different way of thinking about these proofs as mere evidence that probability is a good way of thinking about the world, right? Like Dutch book arguments don't mean that you're only justified in thinking probabilistically when there's some bookie following you around trying to make bets against all your beliefs. There's many different frameworks for thinking about probability. Like, people focus on the Kolmogorov axioms, but there are many other treatments that people have come up with over the decades. And they have a sort of convergence on one picture. Like, these different assumptions tend to yield very similar pictures. And so each of them is individually like evidence that this is some kind of robust structure that we can come up with, right? And so similarly, I'm like, these decision theoretic results I'm talking about are like sanity checks. If the decision theory failed to tile in these simple cases, then we would think, well, it doesn't have much hope for the real world. Our job, in my view, is kind of to make this more and more realistic, to drag it towards the real world, but we have to kind of be patient with ourselves in that process and do things that are feasible before we can do things that have like more realism to them. And so that kind of related to this 1, 2, 3, 4 picture where I'm like, well, 3 and 4 are harder. 1 and 2 give us some tools for thinking about 3 and 4. I've drawn this blue line on the bottom where I think of it kind of as like, you start with informal intuitions, then you can bring the level of rigor of analytical philosophy without any math. And then you can like bring in like mathematical philosophy, but not yet constructive math. It's like things like classical decision theory, which assumes unbounded computing power, things like AI, XI, which assume unbounded computing power. And then we bring it into like constructive math, which adds another layer of realism where things actually have to be computable, but they don't have to be necessarily like feasibly computable. And that's like logical induction as contrasted with Solomonoff induction, say. And then we bring things towards actual implementation. And each of these jumps is like significant and require quite significant cognitive labor. But also, each of these kind of intellectual communities has a pretty serious gap between it that can be difficult to jump. And so a crux for this type of research is how much you believe that we can jump these gaps, particularly the gap from mathematical philosophy, which is sort of where we're at. We're kind of on the bridge already, but like, how can we really bridge from mathematical philosophy to computer science? Is a big question, and particularly like thinking of timelines, can we do it fast enough is a big question. But really, this line is of course oversimplistic. I've drawn double arrows because I think really all of these areas need to dialogue with each other, right? Like, a problem that can be understood at any of these levels or in other ways that I haven't named. We would like to be able to dialogue with all the other levels and like understand it in different ways and be able to address it kind of at each level. So that's how I think about kind of the field broadly and the intellectual pipeline that we need to form for these ideas.
I have a question.
Yeah.
How constructive do you think these constructive math actually is? Like, for example, logical induction is computable.
Yeah.
But does that necessarily mean that it will be relevant when we think for like AI implementations?
I mean,
Like,
to
the
me,
link is not so clear to me.
So one way to think about it is that logical induction uses this big fixed point, of course, that is one part of the computational cost that makes it infeasible. And you can think of it as like the fixed point is a mathematical model of the observation in the world that markets tend to markets tend to be like display some equilibrium properties, I guess I could say, like not that markets display global properties of actually being in equilibrium, but at least markets kind of close, like sellers meet buyers and we get prices out of it. And so that would somewhat justify, just when moving towards implementation, thinking in terms of market analogies and developing systems based on these market ideas. But we can also take it further, and like logical induction, by virtue of using this nice fixed point, gives you like quite good rationality conditions, but we can construct markets in ways that are still rigorous, so still give us some formal guarantees, but are more efficient, and so give some degree of formal guarantees, but not as much as you would get from the more computationally expensive Brouwer fixed point that logical induction uses. And yeah, I could say some more stuff about that, but I don't think I will right now. Paul? Oh, it seems like you're muted.
There we go. Just audio issues on my end. So for a wider question here, it looks like this pipeline you've sketched out at the bottom, that's not something that's just unique to logical induction, say. That's something that you could say is equally, or maybe not equally true, or maybe not in full. Or I guess it's, depending on where it is you're starting your pipeline, but this is something that looks to apply to a bunch of alignment paradigms, or not really paradigms, but like all these neat mathy tools that people are using to an extent and having some trouble turning into implementation.
Yeah.
Impressionism is getting stuck around about the same bridge, maybe getting a ways into constructive math.
Yeah, I think there's like a big gap between theoretical computer science versus applied computer science right now.
Yeah.
Where like there's all this like machinery in theoretical learning, like learning theory, like thinking about like the learnability of various classes of problems and all these like theoretical results. And then there's neural networks, which just sort of ignore all of this and like have a much more experimental mindset, but not just experimental. It's like, I would call it an engineering mindset rather than a scientific mindset, a focus on achieving or surpassing the state of the art, as opposed to understanding the space of possibilities and like why things work and when things fail, and like experiments in the sense of making hypotheses that yield predictions and testing them, and like it kind of like, I don't know, this is like feels kind of politically incorrect or something, but I feel like there's this whole class of machine learning research that's like trying to look like science but is really engineering.
Yeah.
And so yeah, it's hard to bridge that gap.
Okay. I mean, I think I was initially going to ask about, I think something like, do you see some way of, I mean, not really automating bridging this gap, but to what extent is trying to figure out the tools for doing that more formally instead of just ad hoc, whatever works for each specific idea, if that's something you've thought about at all?
Yeah, I mean, so this kind of falls into the class of stuff that while I was working at Miri, I just like wouldn't talk about publicly, because it's capabilities. Um, and as a result of not talking about it publicly, I also thought about it less. But obviously, it's a critical time to be thinking about it. I still feel kind of uncomfortable and uncertain about exactly how to talk about it publicly. So I guess I would prefer to talk about it in at least a slightly smaller group of people. But yeah, I think it's pretty important.
Okay.
So one sort of assumption that I'm going to make, and maybe the name might be confusing, so I wanted to preempt that confusion, is a fairness assumption. So I'm going to call some of the technical assumptions that I make fairness assumptions. This terminology is a descendant of ideas in the timeless decision theory paper by Eliezer. And I don't know if he got it from somewhere else, but a decision problem is unfair if it depends on arbitrary internal details of the agent, such as whether the AI is written in Python or C++, or like which decision theory it's using as opposed to what conclusions that decision theory comes to. So the idea here behind calling it unfair is like, in the game that philosophers play when talking about decision theory, it would be unfair to bring up these kinds of problems as counterexamples, because in this way you can construct a counterexample to any target theory. Right? And so you don't want to be like forced to kind of deal with this problem of, oh, what if Omega just hates your decision theory in particular and calculates what that decision theory does in this problem and then punishes it, right? That's not a fair problem. And so it's not that we expect the world to be fair, but it's that we need to assume fairness in order to realistically be able to make progress. So again, that's one of these things that's like a sanity check. It's like the decision theory should work in fair situations. We know it will fail in some unfair situations, but we want to show that it works in fair situations, and then do sanity checks for unfair situations to see if it at least fails gracefully. Mateusz?
Yeah, so it sounds, so I get the idea. It sounds like you're basically trying to say we're not we are not trying to like evade the no free lunch theorem for decision theory, basically.
Yeah.
But so I get the intuitive idea, but do you have like any idea like how would you formalize the notion of fairness in this sense?
So I think it depends. Like this is a parameter of a theory. I think there's room for some disagreement about exactly what constitutes fairness. Like updateful decision theories are going to be more interested in notions of fairness that are about the decisions that the agent actually makes in the real world, by which I mean the hypothetical decision problem. Updateless decision theories emphasize the importance also of counterfactual decisions, which the agent might not actually make in that decision problem, but which the other intelligent beings in the decision problem might simulate, right? So like when there's like omega in counterfactual mugging, like omega comes and says to you the coin has landed tails, so I'm asking for $10. But if the coin had landed heads, then I would simulate what you say in this example and give you $100. It's like we want to count like what decisions you make in hypotheticals as part of the decision problem as well, because they can influence the decisions made by entities that are thinking about you in this way, that are simulating you or predicting you. And so for updateless decision theory, fairness is more about the policy. And then you could imagine other notions, like this is not the approach that I will be suggesting here, but in trying to integrate updateless decision theory ideas with computational uncertainty ideas, you don't want to depend on totally arbitrary aspects of the cognition, because that's unfair, but you might allow other agents to depend not only on the policy, but on how long it took the agent to think to arrive at that policy. So that if the agent takes a long time to reach a conclusion, then that conclusion is less predictable to other agents. And you might include that as something that's fair, whereas it would be ruled out as unfair by the sorts of assumptions that I'm going to articulate in this talk. But later, if we can ever get to the slide, of course. Any further questions on that?
No, thanks.
So I'll walk you through my notation that I'm going to use. So we have O for observations, A for actions, and we're also distinguishing a subset of the actions that are available upon seeing each observation, so that this is like a sort of like a decision tree in the sense that like each state that you might be at, each observation that you might be at, specifies which actions you can take at that observation. And then, so I'm using script A for the actions and regular A for the the function that represents the agent. So the agent takes in an observation and produces an action. And then pi for policies, which are functions from observations to actions that respect this restriction of the action set to particular observations. And then I'm using this funny arrow for individual policy points. So if you think of the policy as a function, I want to also talk about like individual input-output pairs in that function. And then I'm going to distinguish a set of the actions as self-modifying. So a self-modifying action comes with a set of these policy points that it's modifying. So it's saying like, like if the agent takes this action, then in the observation, oh, it will now do A instead of whatever it would have done. And then I want to talk about the effective policy. So if the agent, by virtue of its decision procedure, chooses a policy, pi, that is to say the function A is equal to pi, then that doesn't mean that that's like what the world experiences, because some of those actions in pi might be self-modifying, right? And so the effective policy is the policy that we get by looking for all those self-modifying actions and sort of unrolling them to get a version of the policy that doesn't contain any self-modifying actions, but already like takes all of those self-modifications into account. So I call it the effective policy because it's, if you choose pi, then it's as if you chose m of pi. And then I'm also going to kind of abuse that notation for individual actions to say like m of A is the non-self-modifying version of action A that could have been self-modifying. Mateusz?
Yeah, but it seems that like effective policy is more like a function from sequences of observations to sequences of actions rather than from observations to actions, because it depends on the order, right?
Yeah, this is this kind of the star that I'm going to talk about.
Oh, okay. Oh, yeah, makes sense.
Yeah. So yeah, I want to say observations include all memory, and so we shouldn't need to talk about sequences of observations. But as Mateusz just brought up, we kind of do need to, because if you self-modify at a certain point in time, then presumably you only influence the future, not the past. So you can't modify parts of your policy that you've already executed on. And so that's why I'm making that restriction of actions to particular observations, because I'm just going to say, well, if at time t, like say you get out of bed and then the first thing you do is you try to self-modify so that you don't get out of bed, right? Like that's not going to work because you can't influence the past. And so I'm treating this as just part of the decision problem, that after you get out of bed, that action of self-modifying to not get out of bed is not an available action. So yeah, this, I don't know if this is like the perfect formalism. I mean, it's definitely not the perfect formalism, because this formalism forces me to assume that self-modifications are deterministic, that we just know exactly what set of modifications are feasible at a given time and which actions enact those self-modifications. And whenever we choose those actions, it just 100% works. But that's the simplest formalism that I could come up with to address these problems. Yeah, any questions on that?
Wait, so M, so notation wise, M is the, or M of pi, is that the policy when pi has done any self-modification that it wants to do in any situation?
Yeah, it's like, so I'm saying you run a self-modification
Mhm.
by, you look at the self-modification, you look, okay, where else in this policy is it modifying?
Mhm.
I substitute in those modifications, and then I replace that action by the non-self-modifying version of that particular action. So the idea here is if I have to take a screwdriver
Right.
to my head to self-modify, then I can also like pretend to take a screwdriver to my head so that it's the same in the outward world. Any outward consequences still happen. And then the definition of M of pi is that I just keep doing
the
that.
thing that I would have done
And then
if I had screwed.
I keep doing these substitutions. I keep looking, okay, is there a self-modifying action remaining in the policy? Then I replace it with the non-self-modifying version and replace whatever it modifies.
Okay, so if it's like,
And so then,
okay, so I come across a situation where I would have wanted to cut my leg off, but instead I just don't do that and hop on one leg forever anyway.
no, so like maybe I'm not understanding your question quite, but let me try to rephrase. So like if I would have wanted to cut my leg off, but I may, at some point earlier, I make a pre-commitment, which I'm viewing as a self-modification. Like I'm like, okay, I self-modify
Right.
so that in cases where I want to cut my leg off, I don't. So my policy,
Mhm.
my like chosen policy cuts my leg off.
Mhm.
But it also self-modifies to not cut the leg off. And so, and it does that before,
Mhm.
like it does that in an opportunity where that would actually work. And so the effective policy is going to be one where I don't make the pre-commitment, I don't force myself, but I also don't
Okay.
cut my leg off. So I just, even though I'm like tempted or whatever, I just don't, right? Like that's
And the effective policy
is I don't
I
cut
don't
my leg
cut my leg off, even if I never encountered observation which would have triggered a pre-commitment.
off. That's where it gets tricky. So like I basically I'm saying, well, we arrange our decision problems such that we never have that problem.
This is the definition.
Right? Like
This is the definition of the question. Like you can like how do you define it?
Yeah. So how I define it is that if anywhere in the policy I make that pre-commitment not to cut my leg off, then in the effective policy I
Right.
don't cut my
Okay.
leg off. So yes to that, but then I'm going to arrange the decision problem such that I don't have the opportunity to make that pre-commitment post hoc, right? Like I don't have the opportunity to make that pre-commitment in a place where it doesn't have the causal influence. So it's part of the sort of causal coherence of the decision problem that this will only happen in cases where it is before we have the
because
opportunity to
once
cut our leg off.
it's identical, it doesn't really matter.
Otherwise, you get like acausal phenomena that don't make sense. Otherwise, you can have like circles of self-modifications that never terminate. Yeah. Or you can have like things that do terminate, but there's race conditions where if you follow this chain of self-modification, you end up in one place. But if you prioritize other self-modifications first, then you end up in a different place. And so you have a unique solution. And I'm just assuming all these problems away, saying we just don't give the formalism the opportunity to mess up in those ways. Roman?
Is there like a mathematically formal way, like can we have a restriction on actions and observations such that this will hold place, like some kind, like you said, temporal causal coherence? Like how does it looks mathematically, besides like such that this problem never comes up?
Right. Yeah. I just, like here, I'm just saying, I just want to assume that this problem never comes up. And that's because I didn't want to assume a particular theory of causality or anything like that. But it does, and especially since updated decision theory is supposed to be agnostic about causality, it's not a causal decision theory, it's more in the tradition of evidential decision theory. So it would feel kind of odd to say, well, I need some causality. But yeah, what's going on is basically some causality thing. And so I suppose that there could be some formalism that would maybe give a more clear picture of what's going on by using causality. Yeah. And indeed, I was talking with Norman some about, Norman was interested in working on clarifying this picture of what self-modification is. So yeah, I guess I'll move on. So the definition of updateless decision theory using this notation. So we have, importantly, we have two different versions of updateless decision theory. The first one that Wei Dai articulated was UDT 1.0, or has come to be have since have been called that. And like this shows, like it optimizes individual policy points. So given an observation, we're taking an argmax of what action we want to take on that observation, maximizing the expected utility according to the prior of taking that action upon seeing that observation. But then Wei Dai noticed a problem with UDT 1.0 that in certain cases it would kind of stupidly fail to coordinate with itself. So a simple example of this is like the UDT wakes up two instances. There's one in a red room and one in a green room. And so it has an observation that's like red or green, but it's irrelevant to the decision problem, which is like, now I want you to choose between $5 and $10. But you have to choose the same thing as your partner in the other room, as your copy in the other room, right? And so like if UDT 1.0 has a prior that has some suspicion that the other policy point is going to choose the $5, then it can be worth it to choose the $5 instead of the $10 because it's worried about failing to coordinate with itself. If one of them chooses 5 and the other chooses 10, then I give them nothing. So it's like, so Wei Dai was like, well, it should just choose the $10. Like, it can just do that. And if it does that, then it gets more money. So he specified UDT 1.1, which is the same basic idea, but it globally optimizes the policy instead of optimizing policy points individually. So yeah, does that make sense to everybody?
Yeah, I don't think it makes sense to me. So suppose that I'm UDT 1.0 and I'm in this problem. I'm in the green room. And I know that another copy of me is in the blue room. And I also know that the other copy of me follows UDT 1.0. And
Yeah.
shouldn't just like, how is this knowledge? It's not clear to me that I couldn't coordinate with myself in this case.
So it depends on the prior. It's like,
Okay.
I could have a prior that says the two copies choices are very correlated. I could say, well, they might get different observations. One sees one color of room and one sees a different color of room, but that's irrelevant to the problem. So our actions are very correlated, so there is very low risk of a coordination failure. So I should just choose the $10. I can still maybe like make it more of a problem by making the risk in the case of coordination failure worse and worse, but I can also like, well, never mind about that. Like, it depends on the structure of the probability distribution. But the thing I'm imagining is like, I can have a prior. It is allowed that I have a prior that says that these two choices are uncorrelated or even anti-correlated. Although anti-correlated doesn't really get us to failure mode, since then it's just kind of hopeless. But or I could have, I can have a prior that's just like a strong prior on choosing the $5 for some reason, right? Yeah, this is the really problematic case. Is like, I think that like maybe the $5 is closer to me than the $10, and so I have some prior that's like I'm more liable to press a button that's closer to me or something like this. And so that's where the coordination worry comes in. Definitely we could make assumptions to try to do away with this, and maybe that's what we should do. But Wei Dai's motivation here was like, this dependence on the prior is problematic without any way of specifying like the good prior that eliminates these problems. And it seems like specifying the good prior that eliminates these problems would be more or less tantamount to this UDT 1.1 anyway. It would have to do the policy selection inside of the prior.
Yeah, I see how UDT 1.1 is more robust to this problem, but so the prior you're talking about that makes like UDT 1.1 that may make UDT 1.0 fail in this problem is like, you mean you're talking about the prior on how actions depend on observations, the agent's own actions?
Yeah.
But
it's sort of the self prior, the
yes,
prior.
yes. Yeah, but wouldn't this be like somewhat inconsistent with UDT 1.0, like with the assumptions that you are taking the action that gives you the most utility according to your prior? Because like the most utility you get in this problem is by choosing the $10 regardless.
That's not true. So it would be perfectly consistent with UDT 1.0 to have a like 100%, or maybe we say like very close to 100% belief that it'll choose the $5 in both rooms, because then it will maximize expected utility to do so. So even under this constraint that the prior on selecting actions is consistent with the decision procedure actually used, we can still run into this problem.
Okay.
And then you have to ask, well, where did this prior come from, right? Like, how did it end up with a prior that was choosing the $5? Yeah, I not reading your whole comment, but yes, I also like UDT 1.0 better, as will be very clear in this talk. Yeah, does that make sense?
Yeah,
This
thanks.
is a pretty important distinction. So if anybody's still confused about 1.0 versus 1.1, I do want to try to clarify more.
So, oh,
Okay.
just to make sure that I've
Go ahead.
understood here, the first one is saying the action that an agent takes on seeing observation O is going to be whatever action in that one case out of its action set looks to maximize its expected utility under whatever prior it believes the environment has, or the environment would, under its expected prior about the environment. And the second one is the policy that it picks overall is whichever policy out of its set of possible policies gets it, again, the best expected outcome, given that it has that policy. Is that right?
Yeah.
Okay.
Gosh, I wish we had 2 hours in this slide instead of 1 hour.
Okay.
um,
The one thing I wanted to ask about is, I assume we're not worried at all about the fact that, or about the likely fact that that set of possible policies is going to force us into some horrible super exponential search?
yeah, we're not worried about that here.
Okay.
But it is another reason to like 1.0 better than 1.1.
Okay.
Like, yeah, it's a horrible super exponential search. And it's also like, it's an infinite search if the set of observations is infinite. And so that's also kind of problematic, especially when we start to worry about computability.
Yeah.
So UDT 1.1 feels like it has less ability to exist in a certain way than 1.0.
Okay.
So
Yeah.
yeah. So UDT 1.1 has a very simple tiling proof that applies to it. So we assume fairness. In this case, fairness is that if the effective policy is the same, then the expected utility is the same. Very simple. Like the universe only cares about your actual policy. This is stronger than the universe only caring about what you actually do. Like it also cares about what you do in counterfactual situations, but it only cares about your effective policy. Suppose for contradiction that there's some policy which has some particular action that it takes that's a self-modifying action. So there's some self-modifying policy which is strictly preferred to all non-self-modifying policies. And then we're like, but by fairness, the expected utility of this policy, this self-modifying policy, should be equivalent to its non-self-modifying version, its effective version, and this contradicts with step one. Therefore, UDT will not strictly prefer, UDT 1.1 will not strictly prefer to self-modify. So this is a very simple argument, but it sets up kind of the pattern that we're hoping to. Yeah.
I think I just had an idea.
Yeah.
Has anyone, so could you go back to the previous slide?
Yeah.
Okay, has anyone tried doing something like argmax over argmax? So yeah, take the argmax over the action out of the action set that your policy would make you take.
Can you say that again?
Yeah. Has anyone, so for the right side of these, has anyone, and I don't really know quite how I'd write this down just yet, but has anyone worked out how this would work in the case where we're argmaxing over the set of actions from your action set, and what we're conditioning on is the action that your full policy would make you take here. So like now we're not conditioning on the one action, and
Okay,
we're
well,
also not.
this is
Okay.
like the same, and then what we're conditioning on is different.
Yes.
And so you're kind of trying to take this and then also take this.
Yes. I literally just thought of this approach. It's like, can you do slightly better here by only thinking about the actual action that it makes you take and only argmaxing over that and not caring too much about what your actual policy is up to equivalence under it makes you take the same action in this situation.
Do you mean just looking
So-
at the situations you take? Sorry, that might.
So it's like you have some, is it like you have some notion of counterfactual where like you're like, well, if I take this particular action in this particular observation, then I think my overall policy is going to be this? Like you have some function from actions to policies like that, or from action observation pairs to policies?
Think so. I think I probably need to think about this a little bit more. But I don't have this fleshed out well enough yet. But
Yeah,
think it would be
because
something
what
like
I
that.
would say about that is like, well, this is already probabilistically conditioning, right? Like it's like the expected utility given this is also going to be like the expected utility given the expected policy condition on that, if that makes
Yes.
sense. So then it has to be like interesting by virtue of an interesting notion of counterfactual that departs from the probabilistic conditioning. At
Yeah.
least given my rough understanding of what you're aiming for.
I
So
I
Think about
wanted to ask a question that seems to relate to Paul's proposal. So I don't really understand why in UDT 1.0 we could take this expectation when we do not actually know the full policy. Because like this expectation is like for the whole future, like the reward. So if you don't know what you're gonna do when you encounter other observations, what's this expectation, or is that like contained in the prior? But that doesn't seem
yeah, it's
right.
contained in the prior. I mean, that's how it's dealt with here. Yeah, of course, you can question that way of dealing with it. It's just like, yeah, we in order to form an expectation, we need to have some expectation about our policy. And here we're dealing with that in the Bayesian way, where we have Bayesian uncertainty about it, and we're just taking an expectation over the possibilities.
That just seems stupid. Like you're you already have, you're taking, it's like when you are taking these argmaxes for each observation, you are not using the information that exists in the other branches.
Right. So one thing I like about this is that I'm reasoning about myself in the same way that I'm reasoning about other parts of the world. Like a framework like
Yeah, indeed.
a framework like IXE is doing more what you're talking about, or what you might be gesturing at, where it's like, in order to make this decision now, IXE needs to think about all of its decisions in the future because it thinks about itself differently from how it thinks about the rest of the world. It thinks about itself with this kind of full knowledge, which is possible to do in this abstract mathematical formalism, but it more assumes like a Cartesian boundary where the agent is like this immortal being outside of the world, and it also more assumes unbounded computation. Whereas if, in order to take the expectation, I have to deal with uncertainty about what other instances or parts of me do, then it feels to me more naturalistic.
But it makes the decision theory, in a sense, like manipulable by the prior. For example, the example you gave.
Yep, absolutely. Yeah, so we're over time. I do want to at least just talk about my discussion of this proof. So I'm like, I think this result is very limited and not very good, right? Like because the whole policy is chosen at once by UDT 1.1, there are not really two distinct agents, one of which is trusting the other. Like we don't have this decision point trusting this other decision point. And so this blocks us from studying Vingian trust, which is one of our desiderata here, that we, because we really can't plan everything ahead of time, we can't rely on knowing exactly what the future self will do in order to get tiling results and prevent self-modification. And so as a result, UDT 1.1 seems like not the right decision theory to be using to study these questions. It's just not realistic enough. And so in that sense, I see UDT 1.0 as more promising. And the subsequent slides are going to look at tiling approaches for UDT 1.0. So yeah, that's as far as we get today, I guess. Any more questions or thoughts?
Well, I think you definitely have thought of this before, and maybe it's not so easy. But is there a middle path?
Yeah, that's what we're gonna like. The slides that I have are discussing just 1.0, but the conclusion is basically, yeah, we kind of need some middle path, because this lack of coordination that 1.0 displays really does create tiling problems, right? And so in order to make progress on just 1.0, we need to just assume away those particular tiling problems, which is a pretty big assumption to make and makes those results feel pretty unrealistic. So one of the subsequent talks that I have planned, probably the next one that I'm going to do after I get through these slides, is talking about the ideas that I have for that middle path. And so basically it's like, well, can we make something that looks a whole lot like 1.0, but is better at coordinating with itself. Maybe not as good at coordinating itself as 1.1 is, but maybe good enough to avoid tiling problems or to avoid the more serious tiling problems. And I have a bunch of different ideas that could be worth exploring in that direction. The simplest idea, in my view, is like trying to apply fixed DT, which is, well, it's a whole thing to explain in itself, but like here, we just have the prior, right? Like in this picture, there's UDT 1.0 just has some prior. But in a more logical induction-like context, which is where we want to move towards, the prior is the result of a fixed point operation. And so we have these meta beliefs, which are like functions from beliefs to beliefs, that tell us like which priors are kind of feasible in the first place, that are like these epistemic constraints. But then out of the possible fixed points, we can select whichever one we like. And so in particular, I would say we are normatively required to choose the best one, that is the one that gives us highest expected utility. So this is like the Harry Potter, you can pass through the wall if you just believe in it kind of scenario, right? Like if there's a situation that depends on your beliefs, then you should believe the thing that gives you the most of what you want, right? Out of the epistemically valid beliefs that you could select. And so imagine if UDT 1.0 was using this kind of fixed point selection, then under certain assumptions, it wouldn't face these coordination problems. Think Roman was first?
Yeah. Doesn't this kind of like isn't it unfair to put an agent in a situation where the result depends on what they believe, like, and not what they are not how they are acting?
So you could certainly view it that way. I don't view it that way. I think the like Wei Dai's red room, green room example that I gave feels very fair. It feels like, yeah, that's like a failure, but it does depend on like what the agent believes kind of determines what it can do in this situation.
Also, doesn't like, I mean, I can just at some point. What if I believe that I can? What if one of the priors contains something like I believe that I will now have a lot of utility. Just like this is what I believe right now, and now I should choose that belief system. This is like excluded by something, by what?
Yeah, so this is, I'm calling it the epistemic constraints. So it's like I should only choose beliefs such that if I choose those beliefs, then I expect them to be correct. Like, yes, I could delude myself, but from my position now, I can see that I would be deluding myself, and so I shouldn't choose that. This is, of course, questionable. So you could say, well, in extreme situations, you would, like, if choosing to delude yourself, like, let's say aliens land and they're like, we only ask one thing, just believe that the moon is made of blue cheese. You can leave all of the rest of your beliefs unmodified, and we will help humans achieve human utopia, if you believe that one false thing, then okay, maybe you should modify to a delusional belief. But this is more what I would think of as maybe unfair. Like, well, yeah, I don't know. I don't know exactly how I should draw that boundary there, but I'm like, what I'm interested in, I think, is cases where we can reasonably restrict only to epistemically justifiable fixed points and not to these delusional fixed points. But even if we were thinking of delusional, like we shouldn't, it doesn't follow that we should weigh it, right? Like, because even if we're picking amongst delusions, we know that deluding ourselves into thinking everything is great doesn't automatically make everything great. Mateusz?
Yeah, so do you think that situations where what fixed points are available depends on our prior belief are unfair?
Sorry, can you repeat?
So you said that, okay, we, in your like mix between Udity 1.0 and fixity or something like that, we want to choose like a state of belief that like maximizes our utility conditional on us believing this.
Yeah.
So suppose that what fixed points are available depends on the prior that we start with.
Oh, okay, yeah.
Yeah. So do you think that this kind of situation is unfair?
I'm not sure. I haven't thought about that too much. It's like we start out as Bayesians with like, well, there's just a prior, and then we're making this meta move to fixed DT where instead of starting out with a prior, we start out with we could call it a meta prior that tells us how to map priors to priors. And then we can solve some problems with that. And then you're saying, well, but okay, we can motivate the meta prior, the like before we settle on a meta prior, we need to talk about like what fixed points on meta priors are available, right? And so obviously we can keep pushing this on forever and just be like, well, the same problem recurs again, and so obviously there's no solution here.
Unless there's a fixed point in this hierarchy of meta.
Right. Yeah, which is similar to stuff that Nissan has worked on. Nissan Stinen. And so I'm kind of like, well, imagine like if we're, I obviously I haven't gotten to the slides where I talk about how to combine update with decision theory with logical induction, but pretend that I had. Then we have like this, we don't just have one prior where we face this fixed point challenge. We have a repeated succession of states. And so we're choosing the prior by this fixed point selection. And then we choose the next epistemic state by another fixed point selection. And then we choose the next one by another fixed point selection. And this is very similar to this like infinite hierarchy, right? It's just that instead of building the infinite hierarchy from the top down, so to speak, by like regressing infinitely and then hoping to come back from infinity, we're building it from the bottom up by saying, well, like we kind of keep adding layers, right? First we pick our first fixed point, and then using that prior, that defines our notion of expectation for choosing the second fixed point. And then that helps define our notion of expectation for choosing the third, and so on. And so maybe you can kind of argue that you should resolve it that way. I don't know.
Okay, thanks. I want to see it.
Paul? Oh, your sound isn't working again.
How about now?
Yep.
All right, great. I'm still thinking about the comment you made about what if Omega lands and tells you that if you self-modify to believe the moon is made of blue cheese, that it'll shower you with utility. And okay, what if we got even weird and more diagonal with it, and Omega wants you to self-modify to believe that once you have self-modified, your self-modification will be the reason to incorrectly believe, again, to make it clear, that your self-modification will be the reason that Omega doesn't shower you with utility, at which point Omega showers you with utility.
Sorry, can you repeat?
Yeah. So the original thing was self-modify to believe that the moon is made of blue cheese and win the puzzle.
Yeah.
Right, get showered with money. What if Omega instead asks, what if Omega's demand there instead is weirder and more diagonalized than just believe this obviously false thing? It's believe that your self-modification will cause you to not win the puzzle, even though that's wrong.
Okay.
And also, even though you probably have the option to self-modify back.
Yeah, it seems very similar. I mean, in both cases, if you accept this modification, that gets you then it gets you a bunch of money, and also you have a wrong belief, right?
Right, but in the first case, with the simple wrong statement, you don't necessarily have any immediate incentive to self-modify back. Whereas in the example I've constructed, you have a very strong perceived reason to self-modify back.
Doesn't matter. Like, is Omega just looking at whether you do the self-modification, or is Omega looking at whether you do the modification and stick with it?
I assume it'd be the latter. If
Okay,
yeah,
if
I
it's the
assume it'd be the latter.
if it's the latter, then it seems like we also want to self-modify, like, to believe this, but also delusionally believe that we shouldn't self-modify back or something like that, which is unclear even what it means to believe that modifying back is good, but also believe that you shouldn't do it. So at that point, it just depends on the details of what Omega is requiring of us. Like, how is Omega thinking about us as a rational entity, and is there a way that we can cheat this?
I mean, I think the problem there is we would want our Omega to be quasi-fair and care primarily about the actions that makes us take. But then it seems like there's no consistent way to end up having persistently self-modified ourselves, because either we don't self-modify and we stay that way, or we do self-modify and because of that belief, we self-modify back to the start.
Yeah, so it seems like maybe just a problem where there's no good solution.
Yeah, I think that if Omega tampers with our consistency, then there is no consistent way to think about it.
Yeah.
Yeah, I was gonna like ask about the same thing. Like, if could we just make it a general principle? Is it good to do this? Like, whatever thing that we're studying, like, for example, now it's self-modification. Then the predictor should not like condition on that, because that's kind of the logic for like in timeless decision theory, the Eliezer's paper, like CDT solves the certain class of decision problems and UDT solves the other class, and it's like whatever. I think the phrase you used in the paper is like CDT solves like action determined problems perfectly, and UDT solves like decision determined. So
Right.
I guess like
Yeah, this is like the idea I mentioned earlier of like fairness based on what actions you actually take versus fairness based on policies.
I'm still thinking about the connection with this specific omega conditioning on self modification situation. Whether this is really applicable here. To say that like we're just not trying to that problem is just not within the scope of within the class of problems that we're supposed to be able to solve.
Yeah. Like I can answer these questions of like, oh, what do I think you should do in these problems? But mostly I feel like they like in order to prove nice theorems, we need to rule out some of these cases. Of course, exactly what we need to rule out depends on exactly what we're trying to prove. All right, well, we're half an hour over. Should we end it here?
Sure.
All right. Thanks, everyone.
Thank you.
Thank you.
Thank you. Goodbye.
Thank you.